Don't kick it. Boss. So I can't even pass this side anymore. So allow me to pass. Let me just pass. All right, so good morning again. Madam Sally, did you have a word with your colleagues? When are you writing our tests? And I understand that this week you are writing your Cat 2s. Huh? Or Simulemba Vinango? So when are we writing which one, on which dates and the times? How many weeks are we remaining with? So this is like next week and the other week? What was the last thing we're supposed to do? Hydraulic structures, huh? Yes. Okay, so we're here today. And I'm hoping that we close this chapter today. Then whatever will be coming or whatever will arise, we'll deal with it accordingly. But today should be the last. So we just have a few formulas that we need to look at. And then we'll have one or two examples to apply the formulas themselves. All right. What do you remember about the last class that we did? What are sewers? Or what's the difference between designing a water main and the sewer? Because I think that's one point that we talked about so much, right? We say sewers, when you're designing sewers, it isn't as much different from when you're designing for the water mains, except there's some properties that you consider if you're designing for a sewer. What were those properties? Was this last week or 2 weeks ago? Last week. Nah, last week we didn't meet, did we? Which day was that? Friday. Last week, Friday? Okay. I've really stretched myself. I made it here on Friday last week. Yeah? What properties? Yes, sir? Presence of particles. All right. What else? What about pressure?
So as a design in such a way that the movement of waste is coming by gravitational force. So they are designed in a structure with its gradient.
Okay.
Sure.
So what's the problem with having a pipe at any angle?
Probably there will be.
So we lay a pipe that is transporting waste like that, and then we have another scenario that looks like it's transporting waste like that. From these two possibilities, what could happen here to a pipe, obviously? What problems are you avoiding?
We are
Here. So two scenarios. This is the pipe. This is your sewer. All right. And this is coming from, we say there's what we call the self-cleansing velocity, right? There's the rate at which you want your fecal waste or your waste to just move in that format. But then you cannot just guess the gradient. You have to it's not even making a triangle. You have to calculate it. So we said if you just guess and then you make your sewer a little bit too steep, what will happen to your pipe? Okay, what will happen to your pipe here? Ha. Hey, I'm marking this test. I can see people are not studying. What's the difference here? Yes, madam.
Just a check. You said last time you said people waste contains a protein. It has a lot of it. So you also say that it needs to be laid at an angle because you want the pipe to be clean so to avoid discarding. So if you said if we lay a pipe like this, we are like the B.
Which pipe, A or B?
We are likely to experience clogging one because the slope is not that much for the pipes to be cleaning up themselves. Then also the pipes are likely to burst.
Did we get that? So the difference between laying a sewer pipe in that format and that format or that format without considering calculations or the characteristics of your waste is that this one is too less steep, so you are likely to experience clogging. Because remember, you don't have a pump that is pushing the fecal waste. You're relying on gravity. So if gravity isn't enough, if there isn't enough gradient, then you're likely to clog your pipes. But with this one again, you cannot just put it at any angle because there's sediments that you're carrying inside, and because of that action, abrasion gets to happen, and so you expect that your pipes would, in a short while, probably burst because that fecal waste is just... Okay, so let's continue. So I think we left it on hydraulic formulas for design of sewers. So for academic purposes, there's always a formula that you can use to, one, determine the velocity, two, to determine the sewer, diameter, but then also a formula that will help you determine the gradient. So those parameters are really important, and then formulas are different depending on what you're dealing with. All right. All right, so let's talk about the factors affecting so flow of sewage. We agree that sewage is just what we are transporting, right? Not so. Okay, so ideally when we're stating things, if we have explained on them, well, that's well and good. If we haven't, you find time as a student to just expand on them. So we are going to talk about the factors that will affect the flow of sewage. So if we're transporting sewage, what are some of the things you should look out for if you're designing? As engineers, this is our only calling, okay, if I can put it this way. You always, before you design something, you always anticipate what could go wrong. It's just as simple as that. So in short, we are that statement where we say there are people that always find a problem in every situation. That should be a part of us. Like, we can't just be positive that our sewer network will work perfectly, we have to think of what could go wrong. Are we together? So if you know what could go wrong, then you can decide, you can design something that would counter whatever could go wrong. So one, what could go wrong or what could affect the movement of sewage? Characteristics of sewage, okay? Of sewage itself. So the makeup of the sewage will affect how it is moving in the sewers. So ideally, before you even design a wastewater treatment plant, you're supposed to understand what will be coming into your plant. If you understand what it is, then you will design it accordingly. So two, conditions of flow. Conditions of flow. Do you remember our conditions of flow in hydraulics? Is it hydraulics? Yes. That was hydraulics, right? I think hydraulics, that still came back in irrigation. Did you do it last semester or are you doing it now? In pumps and pumping. Okay, so they are very much related. I think even in this, you hear some of the common people that coined some of those phrases. The third characteristic or the third factor that could affect the flow of sewage is the cross-sectional area of the sewer. Remember, a sewer is just a pipe that transports sewage. All right? Cross-sectional area of the sewer. Cross-sectional area of the sewer. The fourth one is presence or absence of bends. Presence or absence of bends. We know what bends are, right? Comma, obstructions, etc. Presence or absence of bends, comma, obstructions. So ideally, if you know you're not using a pump as your energy to move fecal waste from one point to the next, you want to have and plan your source of your fecal waste. Okay, so your source, and let's say your ponds, try to have it as straight as possible. Okay, you can still have bends, but even how you put your bends, you cannot just make that 90 angle degree. You can have something that is maybe 120. Okay, so that you avoid mwana monga mambo kampe na munai. Okay, so there's that part. Then the fifth one is roughness of interior surface. Roughness of interior surface. So the material that you pick as your sewer, okay? The material that you pick as your sewer affects how you get to transport the fecal waste. So ideally, I think you want something smooth, right? Because if it's smooth, then there's less friction, there's less abrasion. Last but not the least, we have the slope of the sewer. The slope of the sewer, which gives you the gradient. So those are some of the factors you want to consider when you're designing. So I said slope of sewer. Mm-hmm.
Instead of using bending, that's the reason why they put close to a manhole where this direction, you can bend.
Ideally, yes. Okay, so if a pipe is coming, just having a bend like that, it restricts how much could go on there, or there's just so much that could go wrong. So the best way is where you know there's going to be so much traffic, just open it up, create enough room for things to come, interact, and then they go. But if you can have just a straight path for it, if you can have just a straight path for it, then well and good, because even this itself actually does pose, threats to it clogging. Okay. Yes, sir.
The last point saying that
Mm-hmm. Where? Oh, okay. Uh-huh.
So like what can happen, like there's some places, basically the one which will be based at least which is going down. And the one which is just straight, as for example to say,
Mm-hmm.
the one which is just straight, it will go that lower pressure one, transporting material. So
Mm-hmm.
then what can happen like from the places like Western Province where land is just flat, what can you do as an engineer you are given to construct such kind of a system?
That's a good question. So he has found a problem where there isn't even one. So, ideally, you've done surveying, right? That's where surveying gets to come in. So from wherever, when you're designing a place, before even moving, you're supposed to know the high points and the low points. Okay? But in a case like Western Province, there still could be places that, yes, they look that flat, but trust me, there's some gradient of some sort. But then it's up to you before, let's say, a town is established to identify which one could be a high point where people can settle, and then where you can take that Fico West or the Sewer Ponds itself. If it is just that straight, it's flat, you create your own gradient. Okay? Just create your own gradient. It could be that maybe where you are, so this is your ground level surface. You can either begin to dig, so this is your surface, you can either begin to dig so that you give that slope and it goes, and it has that gradient of some sort, or find ways of elevating your Fico West and then let it just flow and given by a gradient. But ideally, you're supposed to survey the place, know which ones are your high points and your low points, and then you decide. NRDC is a very good example. Where we are is on higher altitude, so to speak, compared to where the Sewer Ponds were. So they didn't just come and say, Zafaka NRDC, no. Of course, they looked at the greatest road. KKVS was thinking of expansions that would happen in the future, even though we're not taking advantage of them. And then they found a place that could have been as high as possible. Then the rest becomes an option. Of course, there are other factors that you consider. Where is the wind of the direction of the wind, for instance? So you don't want to put I think most of the times the winds come from the east, on average, could come from anywhere. So if they had taken the ponds this side, you guys would have been suffering this side, yeah? So they put it on the other end so that when air is blowing, at least it affects Mageza PHI. But then there's a distance, so they can't even tell what's happening. Before you know it, they're just comfortable with the smell as well. But the point is just survey the place, get your high points, look for the direction of the wind, the traffic of people, and then set it up somewhere there. All right. Okay, so let's talk about the empirical formulas. This board is terrible. So let's talk about the empirical formulas. So six common empirical formulas in the design of sewers. So you can just add that on. 6 common empirical formulas in the design of sewers. In the design of sewers. Okay? So these are formulas that, from an academic point, we will ask you to use this formula. Okay? You're still in school. But if you go in the field, you can use whichever one you feel like is working best for the conditions that you have. But there's just a list of them that you can work with. Okay? One, and this is a very familiar name, Chez's formula. Chez's formula. And then we've got Bézin's formula. We have another very common one, Manning's. I remember this so much, I think from irrigation. So Manning's. Okay, the other one is these academicians of the olden days. I don't know what they used to do for life, really. This guy has got mathematical formulas I found at UNZA that were, before you got to the answer, you need at least 2 sides of a page. Kuta's formula. Of course, I'll not bring it here. I don't know what he was doing again, Kumasuas. But he was just everywhere. He's in mathematics. Anyway, it's mathematics, so he felt like it would be everywhere. The other one is Crimp and Bragg's formula. And then this other guy also, I don't know what he's doing here. I saw him in irrigation as well. Hazen and Williams. All these guys have got formulas in here, so. I think these guys had really dedicated their lives to just academia and just a life of studying. That they weren't a part of just a normal society. You know, you grow up, you find a partner, you have kids. Because I think Isaac Newton is one of them. I don't think that brother ever got to marry, really. He was just like into All right, so let's talk about the design procedure. But let me be quick to say that the design procedure we're going to look at here is very basic. Okay, when you go out there, but this is the general format. But because of how time has moved, and I like to think that this book has overstayed in the curriculum. So there are other things that have been, included just to fine-tune your designing process. Okay, so design procedure of sewer. So this is you finding a place like Kumaplot Kujai, and then someone says, can you design a sewer network system? So how do you go about it? What do you do? So one, what you're going to do is formulate what we call zones. So you can say formation of zones. Okay? So what just this means is you want to identify where the markets are, you want to identify where the roads are, okay? You want to identify if there are any other pole lines or pipe, maybe water delivering pipes. So you're just marking out what or which areas your pipes could move. You're also drawing contours. We did contouring in, are you still doing something in third year? It's no longer there. So it got done in second year. Oh. Yeah. So draw your contours so that you know which ones are your high points and which possible areas that are of low points you can take your waste to. Identify where your roads are, identify where the houses are. Do you have pipe networks, water networks that are running through, and then you decide. So those are zones. And once you do that, what you want to do is arrange your sewers, all right? Arrangement of sewers. Yes, madam.
So in a place like in there, which is very much consistent with the group of people, which are other activities that are going on. So you find that maybe you want to design a sewer network system, and there is also a water network system. So provided there's a lot of congestion, is it okay to have them run?
No. So you always make sure they are apart by meters away, because you're always anticipating, like I said, as engineers, we're always looking for problems. Huh? What could arise from this problem? Wait a minute, people are way too happy here. What could go wrong? That's us. So if you put a sewer and a water line like that, there are always leakages. Water could easily interact, and that is bad. So you always, if this is where your water line is, then probably there's an angle that you stay away from. You look at the other options that are there. So it becomes very tricky, especially for unplanned settlements like they are. People have already settled.
Because, for example, when you are going to Yeremia, that side, you find that the sub-mainline of the water network system is even passing through the shore.
Yeah. Yeah, so that means because they came after people had settled, right? So one, they were forced as engineers to say, you know what, we just need to deliver this. So it's up to plot Yamund, supposedly. Because in an unplanned settlement, see the way you've left this piece here? There's one guy who will feel like, hey, that could be my place, my space. How is it that we are not tenga masiapa, so nza tenga pamena? Okay? And he could come afterwards, after maybe you saw this as an open space and then you lay your pipe. On top of it, that's when he comes to build. So it's always tricky. Engineering is one of those professions that there's no blueprint really. There is no one way of doing something. Because whenever you go out in the field, the conditions are always different. And so you have to be on your toes to find solutions for whatever problems that you find there. So you can't go with an already determined solution. Okay, so go there, assess the situation, communicate with them, and then suggest things that you think could work for both you as the people that are implementing and the people that are on the ground. But again, at the end of the day, it's always hard to please both people. Okay, so one party will always suffer. All right, when you're designing the sewer, the other factor you really consider is the quantity of sewage. The quantity. the quantity of the sewage. It's just basically designing for water. Before you come up with a treatment facility, you want to know how many people you're going to be servicing. All right, so for sewers, it's the same. How much waste is coming from a college? So how many people do you think or students will be there in one setting, the maximum you can ever go to? And when you do that, you anticipate how much waste will be coming out. Then the velocity of flow. I think on the velocity of flow, we discussed and talked so much about it. They are what you call the minimum and the maximum flow of velocity. There is a non-scarring, there is a non-blocking velocity that you need. And so we came up with a formula the last time we met, but then there are other formulas that we're going to get into. So the speed at which the fecal waste is moving is really important to us. It can't move too fast because there will be friction, and then you constantly begin to change your pipes, which is bad. But again, it can't move too slow because you're likely to block everything. So we had a formula last time where we said with this formula and given the conditions, you can decide the velocity that works. Yeah. Last but not the least, when you're designing, you need to consider the section of sewers. What do they mean by section of sewers? So this is just some engineering language now. What is a section of a sewer? What do they mean? Engineers. You know what you guys already done in school. At this point, if there are things you don't know in the world of work, you really should be getting interested. Okay, see, Nadia. Okay, so let's try to look at some Okay, let's do just typical examples. Sir. Anika na energy, sir. Come and just erase something here. Okay, so typical examples I'm going to dictate. Kaya and the perform. So sawa nika munga very important. So typical problems of design of sewers. Typical problems of design of sewers. Typical problems of design of sewers. So typical problems of design of sewers. So calculate the velocity of flow. Cheers, my guy. Calculate the velocity of flow. Calculate the velocity of flow. Calculate the velocity of flow in a sewer of diameter 1.2 meters. Calculate the velocity of flow in a diameter of 1.2 meters. Are we there? In a diameter of 1.2 meters. The sewer is laid at a gradient of 1 in 400. The gradient is laid How many weeks are we remaining with again? I haven't taught like this. The last time I remember being this consistent is when I was still trying to impress my HOD to give me a full-time job here. You know how it is. We were campaigning as well. You know. Okay, so the sewer is laid at a gradient of 1 in 400. So 1 over 4. The sewer is laid at a gradient of 1 in 400. Full stop. What will be the discharge through this sewer? What will be what will be the discharge through this sewer? What will be the discharge through the sewer when running 1/2 full? When running 1/2 full. When running 1/2 full. When running 1/2 full. I'm going to explain what that means. When running 1/2 full. Assume N. So just capital N. I'm going to explain what that is again. Assume N is equal to a 0.012 in Manning's formula. Then we can talk about the solution. Okay, assume N, so just a capital N in Manning's formula. So, a couple of things I want to address from here. I think everything is okay up until we are saying 1/2 full. When they say 1/2 full, and probably this is the point that we didn't touch on. If we are relying on gradients to transport fecal wastes, we cannot run that sewer or a pipe at full throttle. You understand that, right? Like you can't fill it up all the way. Otherwise, it's going to clog. You don't have a pump, you don't have an energy that is transporting, so you can't fill the whole lot of a cross-section of a pipe of a sewer. Ideally, if you have a sewer network, it always runs at maximum half. Okay? So this is half full. This is what they mean by half full. Your pipe, your sewer is running at half full. And talking about this topic, whether the question has stated it or not, this is just something you need to know as an engineer, that our pipes transporting sewage are always at half full. Unless I've stated the value. If I haven't stated, then you always consider that, and this is what's happening. So you've got your fecal waste running, and then this is left bare out there just to avoid clogging. We good? Okay. So solution. So the question already says N in Manning's formula. So of the formulas that I stated there, you go back to which one is Manning's formula. Your role, your job is to look at all of the 6 and understand which one is which. In an exam test or anything, I will give you maybe 1, 2, 3 formulas. And then it will be up to you to decide, okay, he said Manning's, of these 3, which one is it? Tomfana? If I want, I will give you the whole lot of the 6 so that you can decide which one is the Manning's. So let's imagine that we know what it is. So Manning's formula looks something like this. This is velocity is equal to 1 over n. There is an m 2 over a 3. There is an I raised to the power 1 over 2. So find time to look at all the formulas that we talked about. And what will be so common in those formulas is that the V, which is the velocity, will just be the same. The M will also stand out, and then the I will also stand out. So you need to identify which one means what. So the question said find the velocity, not so. So according to Manning's formula, this is your velocity. This is Manning's coefficient. What is M? All right. So if you find time to look at your M, we may have skipped this point. Okay, so M is known as the hydraulic mean depth. Okay, hydraulic mean depth, and how you find it is always what is the area of the pipe you're considering. You're dividing this by perimeter. When last did you hear this? Perimeter. Okay, but then there's a way you can simplify this. What's the formula for area? Pi diameter squared over A4, right? If we're going to divide this, what's the formula for a perimeter? But not with an R, but with a D. Okay, the one that we know. What is the formula for perimeter? Mwadilaba? What's the formula for perimeter? Yes, because these are secular. The perimeter of a circle. We didn't do that. Eh? 2 pi r. Someone to Google that. So it's supposed to be 1 over pi diameter. All right? But I want the original, the one that has got r's. Should be 2 pi r squared. It's 2 pi r.
2 pi r
In a circle, right? So 2 pi r is equivalent to pi d. Right? Okay. So I'm trying to break down what the hydraulic mean depth is. It just means area over a perimeter of your pipe. If your area is pi d squared over 4, the perimeter is pi d, what you end up with as a simplified formula for M is just a diameter of your pipe you're considering over a 4. Because these guys will cancel each other like that. So d over a 4. So whenever in the formula, of which this will happen everywhere, whatever formula you're dealing with, if it has got an M, this is how you deal with it. So, meaning my M is equal to, what was the diameter? Over a 4. I can just leave it there. My N was given as 0.012. What is my I? So your I is just your gradient. Are we together? We're trying to find this. So we know what that is. We know what that is. Your I is just your gradient. And so let me say gradient, because it's the first example. The gradient given was 1 in what? 400. Once you have these figures, then it's just basic mathematics now for you to just plug in, right? Okay. So meaning your velocity will be equal to 1 over 0.012, multiplied by, we're good mathematicians, I'm not worried about this, 1.2 over 4, we're raising everything to a 2 over a 3, multiplied by the gradient, which is 1 in 400, raising everything to a half. Is this okay? The statement, this pipe is running half full. How does it come into the... How does it come into the formula? Mm-hmm. Half full. What do we do with the half full? Because it exists for a reason. So why are we not seeing the half full written somewhere? Mm-hmm. Anybody? What do we do with the half full value?
So maybe after you find the answer, you divide it by 2.
After you find the answer, you divide it by 2. Anybody else? Anybody else? So you're right. Okay, whatever answer you're finding here, you are also just dividing by half. Okay, and that should be your answer. The module, I think on the... Someone just to punch this as well, trying to look at question number 2. I want to find this answer, but the last time I remember punching this, there should have been a mistake in the module. So the module's got a wrong answer, but ideally you're supposed to put a half somewhere. Mm-hmm. Which one? Like here? Or like you put it no, you don't. You don't put it here. Okay, so without the half, what value are we getting here? So according to this, it says 1.867 meters per second. So this is your velocity. The half comes in really important when someone says, if you have your velocity, can you now give me the discharge through that sewer? What's the formula for a discharge? Discharge is equal to what? Right? So this is where your half will now come in. So your discharge now will be half of the area. So what's the area again? Pi, diameter was 0.2 over a 4, right? Multiplied by the velocity that you have found here. 6.7. Okay? So it's area by velocity, except your area wasn't full. You weren't transporting the fecal waste at capacity, but only half. So this is where your half is coming in. I know the question didn't really ask us to find the discharge, but ideally that's where it's leading you. If you find the velocity, then the next question someone asks you is, what was the discharge in the sewer? So if you did your math correct here, you bring it here, you should have a 1.056. What are the units? Per second. So usually, the moment you find your velocity, then discharge will be found as well. So the half full was emphasized because they anticipated you knowing that you need to find the discharge. Okay, so that's the simplest of the questions you can ever find here. Let's just do one more. What time is it? 9. Okay. So just one more, and then the rest of the questions will just oscillate between the simplest and what we're going to look at right now. Sir, who's futako na? Just that side. Can we confirm these values? They're okay? Okay. So just identify where you're bringing the half when you've been asked to find the discharge. Supposed to be 7? Like here? Okay, anyway, I'll still mark you 2 decimal places that are correct. I will still mark you correct. Okay. So allow me to repeat this. Your task is to know all the formulas that you can identify them, because you're going to be given the ones that will be useful. So it will be up to you to say, this is the Mannings, this is the Shezes, this is the Hazen and Williams, and I'm using it in that way. Calculate the velocity. This is problem number 2. Problem number 2. So I can say problem number 1. Problem number 2. Calculate the velocity. Calculate the velocity, comma, discharge. Calculate the velocity, comma, discharge, comma, Shezes coefficient. Shezes coefficient. Shezes. We wrote this. Calculate the velocity, discharge, and Shezes coefficient. Oh boy. For a stoneware sewer. Stoneware. Stoneware sewer running half full. For a stoneware. For a stoneware. For a stoneware sewer running at half full. Full stop. The diameter of sewer is 150 millimeters. The diameter of sewer is 150 millimeters. The diameter of sewer is 150 millimeters, and it is laid at a gradient of 1 in 60. And it is laid at a gradient of 1 in 60. It is laid at a gradient of 1 in 60, full stop. Assume n, which is the capital N, equal to a 0.013 in Manning's formula. Assume n equal to a 0.013 in Manning's formula. Are we there? So just getting the data from the question, I am hearing that I need to find myself velocity, I need to find myself discharge, and I need to find myself Shezes coefficient. Shezes coefficient. Okay, it's a question mark. What I'm working with is that it's running at half full, obviously. full. They have given me the diameter as 150 millimeters. And my gradient, which is just R, is 1 in 60. So, if you understand the question, also there's an N, which is Manning's formula, 0.013. So if you have understood the question, there's Manning's formula, and then there's also what? Chase's formula. So you need to, at one point, use the other so that you can find the solution. What will work first is your Manning's formula because it's got all the factors, okay? If you go to, so let's do this. So for Manning's formula, we said it's V is equal to 1 N M2 over 3 gradient 1 over 2. Chase's formula, however, so I didn't give you, but just find time to look through it. Chase's formula looks something like this. It's also a velocity being equal to Chase's coefficient, denoted by a C, capital C. A square root is got an M, which is a hydraulic mean depth, and it's got your I, which is just a gradient. From the given data, the information, you can't go and make use of Chase's formula. Why? Because your C is unknown and your velocity is unknown. So what you work with first, the gradient you have for Manning's, the M you have because the diameter has been given, the N has been given as well. So here's how you go about it. Use Manning's to find the velocity. Are we together? When you find the velocity, come and plug it in Chase's and make C the subject, then you find your answer there. Okay. All right. So let's find the velocity and the discharge using Manning's, and then for us to find Chase's, we just come and switch. All right. So velocity looks to me like 1 over a 0.013 multiplied by, what is our M? So M we said was a diameter over a 4. What is 150 divided by 1,000? 0.15. 0.15 divided by 4. So we're going to plug this in 0.15 divided by 4. Everything being raised by 2 to 3 multiplied by, the gradient given was 1 in 60, raised to the power 1 over 2. If your math is correct, and find time to just confirm this when you go back to your room. You've got a question, sir? Yes, sir.
Why have you divided it by 1,000 there?
So we are in millimeters. Everything has to be worked in the SI units. So convert every distance to a meter. Yeah. Tom Fan, that's a very good question in observation. Because my exam zakafaka, okay? But notice the units, because at the end of the day, your velocity is a meter per second. So you can't get to a meter if you have been working in millimeters. So if your math is okay here, you should have a velocity of a 1.1 0.13 meters per second. So that's your velocity. But then we know that the moment you find your velocity, it's easy to find yourself a discharge, which is area by velocity. So our area is pi 0.15 raised to the power 2 over 4 multiplied by a velocity which you have found, multiplied by half. We know where the half is coming from because it's half full. Okay? If you went about it the right way, you didn't make a mistake, you should have a discharge. Where is the discharge again? So a discharge of a 0.01 cubic meters per second. So notice how these are linked. If you make a mistake just on the velocity, it means your discharge will be wrong. It means your Chassis coefficient will also be wrong. Are we okay so far? Yes. So having found this, you already have your velocity. Just go back and identify the formula known as Chassis formula. Yes, sir? On the what? Uh-huh. For this example? Oh. It's just basic mathematics, sir. So, what is 4 by 20? It's 80, right? So multiply the 20 as well for 0.15. So you just want to have whole numbers. I thought you guys are good mathematicians. Tambo Ibara. Okay. So having found the velocity, the discharge, from the list that to be given to you in an exam or a test, you need to also identify the Chassis formula. And we said its velocity is equal to a C M I. Excuse me. The M that exists in Chassis formula is the same that exists in Manning's, is the same that exists in Crimp and Bradges and Hayes and Williams and all those kind of stuff. Okay? So make C the subject is equal to your velocity, which is 1.113. You're dividing everything by the square root of, it was what? 0.15 divided by 4 multiplied by a 1 in 60. And if you still remember how